Well, I know that a lot of you are just joining this class now, and so I just want to tell everybody that this is a second semester course, but we're providing review materials for those of you who either really, it's been a while since you took statistics or didn't take it here. So what I want to remind everybody is that there's these, to log on to Lon Kappa right away. So if you're just entering this course, just try to get on Lon Kappa right away. If you can't, email me and I'll put you on so that you can get started with the review. And that will help you understand the lecture today if you're having trouble with it, and the lecture that was given the first day of class right here. We did more than just go over the syllabus. We covered up to page 6 in the notebook. So you can, after every class, I'll embed the videos right on this calendar. And the calendar, just Google Stat 200 or just go to this website. If you don't know how to go to the website, I'll just tell you one more time. You just do go.illinois.edu, and then you just put right here. How come I can't put any more there? So it's go.illinois.edu/stat. What do you think? 200, right? So you do that, and that takes you right here. And this is all the course information. So the calendar is something you should check all the time. And right now, it says that there's a survey due. Bonus survey 1, it's real fun to do. We analyze our own data, and they're anonymous, and they're bonus points, so go ahead and do that. And the review that will help you. And your first homework is due on Monday, and it covers this first week here. Okay, yes? Yes, it does. That's a good question. She asked, if you exhaust all your tries in Lon Kappa, you have multiple tries. I'll tell you under each question exactly how many tries you have. But if you use them all up, the correct answer displays. And even if you get the correct answer, you should look at the displayed correct answer. If it's a numerical answer, because that's in a problem where it has multiple parts and you have to use one answer to calculate the next one, always use the displayed answer. I write that in the directions, but sometimes people forget. Otherwise, you can accumulate rounding errors. So everybody, in numerical questions, everybody's getting a different randomized set of numbers, so you're not getting the same exact as anybody else. So when you're doing it, it's very difficult to adjust the tolerance big enough to both ensure that you're doing it right and not grade you wrong if you're doing it right. So it's difficult. So just use the answer that is given to you. Any other questions? Yeah. What's the range of the tolerance? The range of the tolerance by default is to just answer to 2 decimal places. But otherwise, unless otherwise instructed. Okay? Yes? Will you be able to do homework 2? Is not even posted. Homework 1 by the end of the lecture. You'll be able to do the Monday's homework. You've already done it? Yeah. You'll be able to do problem 2 by the end of the lecture. Yeah. Other questions? Yes? For the exams, you can use any calculator that you want, except one that connects to the internet. You can't use your phone calculator, so go out and buy a cheap calculator. Do you need a fancier calculator? Not really. On the exams, you have to show your work. So even though you might be able to calculate something with a fancier calculator, it won't help you unless you show all your work. Any other questions? Oh, that's another thing. I'm glad people are asking questions. Always interrupt me anytime during the lecture. If you see anybody's hand raised and I don't see it, just say question and I will stop what I'm doing because I love to answer questions. Okay, any other questions? No. Yeah, good. Oh, good question. You see, I forget things, so it's great that you reminded me. I meant to say that you have to bring, okay, so the iClicker is worth bonus points on the grading here. I can show you for those of you who want to see. And we're going to start using, here's the iClicker, it's 20 bonus points. And we're going to start using it starting next week. So get an iClicker, and you can, if you need instructions for how to register it, look on Compass. Now, was that your question? What was? What software to use? Can anybody answer his question? I'm sure somebody here can just ask it. Somebody will be able to answer it. You want to know what software to use for the iClicker? Yeah, go to Compass and follow those instructions, and you'll be able to. Oh, okay. Well, see David right here after class. He'll help you. He's our tech specialist. All right, any other questions? Okay, so we're just going to continue right now. If there's no more questions on the syllabus, with the lecture. So everybody should turn to page 6 in your notebooks. That's where we left off last time. And we're looking at hypothesis tests, significance tests. So this is a question, and we're also not only looking at setting significance levels and looking at the probability of a type 1 error, but we're also looking at specific alternative hypotheses and the probability of a type 2 error. So, okay, so I think my 2-year-old granddaughter Talia is a gifted statistician. To test this claim, I asked her, or I plan to ask her, 100 yes-no questions, right? And the null hypothesis, the dull hypothesis, is that she's just guessing. So just by the luck of the draw, she'll get 50% correct. That's our null hypothesis. I think that she's, you know, that she's gifted and that she can do better than that, even though she's only 2. So now, how much better? So when you're doing these, there's a range of alternatives. I don't think she can get 90% of them correct. I think she probably can get about 60% of these questions correct. So I'm going to set that as my alternative hypotheses. So we have a null hypothesis that says she's going to get 50% correct, and in formal language that's saying that mu, the population mean, is equal to half, 50% here. And the alternative is that I think that she can get at least 60%. You set the minimal alternative that you think could be true. You know, if she could get that I care about too. You know, if it was, you know, I think she can do about 60%. So I set that as the alternative. Okay. So now what we're going to do, the idea is that we have 2 sampling distributions, and the goal of this, first of all, is to calculate this probability of what's called a type 2 error. In other words, if I'm right and she gets 60% or more correct, if that's her true ability, if she gets that, what's the probability that this test won't pick that up, that we won't reject the null? All right, so we got this far, and we said we're going to follow this roadmap that we established last time. We said first we're going to find a standard error, right? We expect right here, there's this sampling distribution. We modeled it, our probability model is that every time that if she's just guessing, then she has a 50% chance of getting it right, and I'll count it as 1 right, or a 50% chance of getting it wrong, which will be 0, right? So I ask her 100 questions, so I expect her to get 50 right, or 50% or half the questions right. But when the null is true, right, she's not going to get exactly 50. There's variation, and that's called the standard error. There's the sampling error. Every time she draws from this box 100 times, that's the null that she's guessing. She's just like taking a box that has a 0 and 1 on it. And every time she draws either a 0 or 1, and then she puts it back, of course. Even if there's 50 of each, you want to put it back because you want to keep the odds for every question 50-50. So she's drawing 100 times with replacement from this box. And there's variation. Theoretically, she could draw 100 ones and get 100%, or 100 zeros and get 100 and get 0%. There's variation. And the sampling error or standard error describes the typical variation. So we'd expect her to get 50% right. And how did we compute that standard error? Well, it depends on two things. The spread here in the box, the standard deviation, called sigma, because it's the population. This is like describes the population. And so this is the population standard error is the square root of 0.5 times 0.5. And that's 0.5. Okay, so if you don't know this, in Stat 100, we often didn't have zeros and ones on these tickets, so we paid attention to this. So we said 1 minus 0 times 0.5 times 0.5, but that's not really needed here. All right, so we did that, and it also depends on the sample size, n. So there's 100 tickets, and obviously, if she just drew a few times, she could get 100% right or wrong. There's huge variation. If she just drew a few times, but drawing 100 times, it's very unlikely that she would get them all right or wrong. The sampling error goes down, and it goes down as the square root of the sample size. And so that's the formula here, SD over square root of n, and that gives us 0.05 as an average. If we want to change it to a percent, like we are here, you multiply by 100. So that's 5%. So this was the sampling distribution of the mean when the null is true. Okay, that's what this is called. You can write that. So this is this, well, we don't have to write that. You know, this is the sampling distribution of the mean when the null is true. Now, and it follows the normal curve. So as you can see, we matched it up here. We said one standard error is 5%. And it all matches up. So this gives the probability, this is 100% of the area. The area under the curve is 100%. So the probability that she'd get 60% or more is that little area right there, which looks like pretty unlikely if she was just guessing. Okay, that's what we did so far. Now our roadmap was we find the standard error, we got that. The second thing that we said we were going to do was we were going to find this distance between 50% and 60% in terms of a z-score. Well, we did it pictorially, but there's another way to do it, and we said we were going to do it. So we're going to find this z-score, this ZD, between our null hypothesis and what our alternative hypothesis is, of the 60, these two right here, this 50 and 60, this distance of 10%, we're going to translate it into a z-score. You see it's 2 here because we drew the picture, but let's say we didn't draw the picture. How do we do this? We just say, okay, that distance of the alternative hypothesis minus the, it's like the observed minus the expected values. This is the alternative hypothesis value minus the null hypothesized value divided by the standard error. So those of you who've had stats before probably recognize a z-score is some kind of usually an observed value minus an expected value over standard error. This is the same thing. I want just as a distance, so I put the absolute value. So I'm getting this distance here. So let's do step 2. We did step 1 right here. That's sigma over root n. We did that. Now, so this is step 1. We got the standard error right there. Now we're going to do step 2. We'd say that the distance as a z-score is going to be 60%, the alternative hypothesis, that can be like our observed, minus what we'd expect under the null, which would be 50%, the absolute value of that, which is just 10%, divided by our standard error, which is 5%. And that equals 2. And you can see when you draw the picture here, we're doing the same thing. We're saying one standard error, this is a Z-score, same as standard units. Okay, so it says, it tells you, so one standard error is 5%. So two standard errors, 60%. So 60% is 10% or 60% here. Okay, does that make sense to everybody so far? Okay, so that's what we've done. You don't have to draw the picture. I just wanted to intuitively show it to you. This would give you, if you're just trying to calculate it, that would give you your answer, right? Okay, but that's the picture. Now, what do we want to do? So we look here, and we're going to try to calculate the probability of a type 2 error. That's beta. But we have to first be given, we set our type 1 error, which is called the significance level. And it's typically conventionally set at 5% right here. So we're going to do that. Set the significance level at alpha equals 5%. For this problem, we're going to do that. All right. So that means that we want 5% in the tail here. We want to get the Z that corresponds to 5% in the tail there. So how do we do that? We want 5% right here. Well, you could use a calculator, a table, or the calculator online. Another way to do it is, I think is a useful, we can use the table at the back of the book, and this is a table you'll be given on exams, so you might as well figure it out from here. So let's turn to the back of the book and look at this table here. So this table is symmetrical. I like it because it's nice for confidence intervals too, and it gives you a good feel for the normal curve. So what do we want to do? We want to find the Z corresponding to we want the picture to look like this. We want 5% in this tail here. And to use this table, and we want to find a Z-score that corresponds with 5% in that tail. But it doesn't, this table doesn't give you the areas of the tails. It just gives you these middle areas. That's what this is. This is on page 253 in your books. These are all middle areas. It's symmetrical. All right, so what would be the middle area then? If we have 5% in one tail, to make it line up and match there, we'd have to make 5% in another tail to use this table, and then there'd be 90% in the middle. So this will give you this, so we want to look up 90%. So you look here, and on exams, it's just simplest if we just round, and doing together in class, I think it's just easier for our intuition to just round. So we'll just round to the nearest line here and say 1.65, even though it's a little bit less. It would probably be 1.645 if you did it on the calculator online. Okay? So that's 1.65. So what does it mean? Between Z equals 1.65 and Z equals negative 1.65 is 90% of the curve. And so that is the Z-score corresponding to alpha equal to 5% for this one-tailed test. We're just interested in that 5% in one tail. All right, so we've got that, and that's going to be our Z alpha. So let's go over here and back here. All right, so let's write that here. And so that's 1.65. That's kind of hard to draw here. This is 55, that's 60. Just sort of accurate. It's more than halfway, about like right here, let's just say. That's Z alpha equal to 1.65. And how did we get that? Just as a reminder, we should write it down here. We used a table. So this is So we just did this. We said, okay, 5%, 5%, we did 90%, and we used the table. And we looked up a Z-score using table, use table to look up Z-score. Look up Z-score for middle area equal to, look up Z-score for middle area equal to 90%. And that's how we got the 1.65. Okay, so that is right here. Find the critical value. Why do we need that? We need that because now when we skip down to, remember what our third step is going to be. Our third step is going to be once we get Z. Our third step is we want to find beta, so we're going to find Z beta first. And so our third step is we're going to find Z beta and then beta by what? By knowing that this ZD, which is 2, is going to be equal to Z alpha plus Z beta. That's where we're headed, to the absolute values of those. All right, but now let's just go back to the problem and think about it. All right, so what is this? This is our cutoff, our decision maker, And what it means is saying that, okay, we are going to decide if Talia answers beyond this point, right? We're going to decide, we're going to reject the null, and we're going to say, okay, she's not just guessing. She's got some talent. So you might think, oh, this is great. 60% is on the right of this, so we're going to be rejecting the null. And so if her true ability is really 60%, we're good, and this test will detect that. But you have to realize that there's a sampling distribution around the alternative as well, right? So when H alternative is true, there's a similar sampling distribution. So this is what it looks like, right? So even though more than 50% of the time we will detect her talent by this test, there's a big area, probability, all of this, where we won't detect it. We won't, even if it's really true, and she does have this ability, we won't detect it just due to the luck of the draw. And this is the probability of the type 2 error. That's what we're trying to figure out here. Okay? So that's the idea. And so let's write, so now we're on step 3. And we know that this distance right here, well, let's just write down this, what we want. So we said this, what we're doing is we're taking this distance between 0 and 2, right, as a Z-score. And this, our decision maker, when we set Z alpha right here, equal to 5%, here's our 5%, we're also setting the probability, we can from that calculate what the probability of the type 2 error is. So when we say this part from here to here, let's just do this. Okay, so this part, Z alpha is 1.65. Well then, this distance right here, this is Z alpha. This, the whole thing adds up to, this whole thing is ZD, and that's equal to 2, the entire thing. So this must be 0.35, and that's Z beta. And that will give us this probability here of the type 2 error. Okay? So this, so let's write that. So we have ZD. We're just dividing ZD into 2 pieces, Z alpha and Z beta. The reason I'm using absolute values is because Z beta is going to be technically negative here. I'm just doing distances. I'm taking this distance, and when I decide on a cutoff, I decide on the probabilities of both types of errors, and there's a trade-off between them. So, so it looks like this. All right? So we know that the distance here is 2, and we know that this is 1.65. So we know that the absolute value of z beta is 0.35. And from that, we can figure out, by looking at the table, we can look up the middle area for 0.35 and then get the tail. So we can get that. And we can figure out the probability. What's the chance that we won't, even when the alternative is true, and she does have this ability, our test will fail to detect it. Okay, so let's do that. So we know that the absolute value of z beta is equal to 0.35, right? So now we're just going to look at the table again. And what are we going to do? We're going to look at the table. And we're just looking at this curve now, this one, right here. And we're saying this little distance, I'll draw it, we have negative 0.35 and 0.35. So we're going to find the middle area between those two. And then this right here is the probability of the type 2 error. So let's do that. And when we do that, you can see that it's completely symmetrical on this table. There's no negatives because you really don't need one if you understand the normal curve. You don't need a negative z. So we go back to the table, so right here. See, there's no negative z's because it's symmetrical. So you can look up a positive z and we'll have the same middle area. So we want to look up z equals 0.35, and we see 27.37 is in the middle. Let's just round to 27. So now we have this is 27 right there. Okay? The whole thing adds up to 100%. So this beta here is going to be 100 minus 27 divided by 2, which is what? 127. So we have 73 divided by 2, which is 36.5. Yes. So this right, yeah? I'm sorry, can I what? How did I get the 0.35? Okay, well, okay, so here, you know, between here and here is 2, right? And all I'm doing with this is I'm drawing another sampling distribution right here, okay? So I'm saying this, between 0 and, when I do this z alpha right here, when I make this, I said z alpha equals 1.65, right? But, so, and I know the whole, so this is 1.65 right here. And now what's this little piece? This little piece, you see what I'm doing here? This is like a little middle area here, and I'm getting, so that little piece is 2 minus 1.65, it's 0.35. Between here and here is 2. So 1.65 plus what makes 2? That distance. It's just a distance. Here, look, you have two curves. One when h naught is true, right? And then you have another one, they're overlapping, okay? And that's when h alternative is true. So, the middle of this one's right here, and the middle of this one's right here. So I get, so this is some distance in z-scores. Okay, in this case it was 2. Does that make sense to you? And then I say, okay, when I do this, decide on this cutoff, I want this to be 5% here. So that made this 1.65. So from here to here, this is called z alpha, and this part is called z beta, and together they add up to 2. Does that help? Okay, That's all. It's not hard. And you see, maybe I can show you on the, you know what might make it easier? And it is to show you a little calculator we made online. So a picture's worth a lot. So let's go here and let's look at it. So it's called power calculation. So we can do this same problem by a power calculation. So we'll say our population mean is what? 0.5. And our alternative, whoops, that doesn't look right, does it? 0.5. That looks right. Okay, and what's the alternative hypothesis? 60% or 0.6. Is that good? Do you remember what sigma was? What the standard deviation was? Of the 0, 1 box? Not the standard error, just the standard deviation. 0.5. So let's put that in. And you can see what I'm doing here. So that's 0.5. And now, let's line it up. And now, what was our sample size? Whoops. Woo, it wasn't like that. Our sample size was, we deliberately did this so you have to figure it out exactly, and it's hard to go, you can't get exactly 100 like the ones that we give you for problems. If I want to get close, sometimes I get really close, like 9. Oh, I got 101. Oh, let me go back. Oh, darn. I know you can get 101. Darn, I can't do it. Oh! Oh, come on. This is too hard. We made it too hard to get close. Okay, oh. Boy, this is really hard. But you can see what we're doing here. We're not getting our, if I could get exact. Okay, look, I'm holding it there. Do you see how we got 30? Our beta was what? Our type 2 error was 36.5. Y. Our alpha is 1.645. It's everything's very close, right? Do you understand? Do you understand also if you change the type 1 error? See, there's a trade-off. Like if I make our type 1 error smaller, our type 2 error gets bigger. So do you see how this Z alpha, when we set it at 5%, our Z alpha was 1.65. But if we set it smaller, our Z, let's say we want alpha equals 2%, then your Z alpha is going to be 2.05. But Z alpha plus Z beta is always going to equal the whole thing. You see how it divides the distance? This distance between 50 and 60% is 2. And our decision, once we set Z alpha, then Z beta is determined. Does that make sense? Yeah.
So for any problem we're given where we have, or this kind of problem that we're given, will either the type 1 error or the type 2 error be given because it's kind of arbitrary?
Yes, the type 1 error is always given. You set that. When you set like, this 5% p-value that everybody, that's setting it. That's your choice. And it doesn't have to be 5%. We talked about that. That depends on the problem, what you care about. But it's typically often set at 5%. And then for a particular sample size, the type 2 error is determined. So let's think about this. Let's think about exactly that question. Because, do we have more, any more questions? I know it's a lot to process, especially if this is your first, if you didn't even watch the first lecture yet. Go ahead.
Besides setting alpha to 5 by convention, is there any other reason, or any reason why you would set it to something different?
Yes, there's a lot of reasons we would set it to something different. For example, if you were testing, like we talked about last time, you probably weren't here, if you were testing a smoke detector, for example, or a fire alarm or something like that, Remember, 5% is the probability of, when nothing's going on, that the smoke alarm might go off. Well, that we don't care about setting it that low. We care about setting the type 2 error really low.
Is there like any formulaic way to do it, or is it just entirely by?
It's entirely by the situation.
Okay, so it's not so much by any mathematical thing. It's just by choice.
Absolutely not by. Well, you don't want to set it more than 50%, right? But I mean, yeah. I mean, it depends on what you care about. How important. What it is a false alarm. All right, is a false alarm really, if it's, you might not care about that very much. Maybe you really care about, let's say it was testing some drug. So what if you have a false alarm if it's not harmful? Maybe the drug could cure cancer, it could be an amazing drug. So you want to absolutely detect if it really does work. You want to absolutely detect that it works. So you do not want to set it so low because there's this trade-off. Now, obviously, the best thing that we really want to do is what? Set them both low. Have them both low. Well, how can we do that? Let's think about how we can do it. Do you see how the way that we can do it is by lowering your standard error? Look at this. Making your sampling error much less. So you have more precision, and then you separate those curves. So you're not going to have those. So both errors will be reduced. See that? If you separate them, you get very small errors on both sides. So you want a bigger experiment to detect, have a bigger sample size, you'll be able to detect with more accuracy, more precision. So let's look at the next page here on the document camera, and that's exactly what we're talking about here. So how can we decrease the likelihood of this type 2 error? Like, this is big. Let's go back here, and we never finished this problem. So let's just make sure we finish this up. Okay, so we have this, which was the type 1 error. We set that at 5%. And that's 5%. Then we have this type 2. And this was equal to 36.5%. That's big. So we want to lower that. There's something else called the power of a test, which is the power to detect a difference that really exists. And the power is equal to 100% minus beta, the type 2 error. So the power in this case would be what? It would be 63.5%. It's all that. That's the power. And that's the power to detect. You want a high-powered test and low error there. All right. So I know that's a lot to digest right now, but let's just think about the ideas here right now. So how can we decrease the likelihood of a type 2 error? We just talked about this a little bit. One thing we can do is let's draw this little picture here. So here's our type. We made it smaller by sliding our decision maker, but in the process, we made this a lot bigger because there's a trade-off. Keeping everything else the same, if you slide this line back and forth, increasing one decreases the other. So increasing alpha decreases beta. But you want them both to be small and vice versa. So there's a trade-off here. All right? So how can we make them both small? Well, we could just slide. What if we just increase the distance between our alternative and our null? If we slide this, say, okay, if we, for the example we just gave, what if we slid 60% up to 90%? Well, sure, a bigger difference is easy to detect, but Talia can't answer 90%. If she could, it would be very obvious she was a genius. I probably wouldn't be doing this significance test. I mean, if in the example I was giving you before, between the ongoing experiment that we're doing right now between the online students and the in-class people, and we're trying to see which method is resulting in higher overall performance, if it was dramatic, like if there was like a 20% difference or something, like they were scoring A pluses and this class was scoring B minuses or something like that, then of course we wouldn't need to do this. I mean, it would be very apparent right away. So we wouldn't, it's very easy to detect a big difference. Usually when we're doing these significance tests, it's because it's not such an obvious difference. So why can't we do this? Is because we have to pick an alternative that corresponds to reality. I can't just go ahead and pick 90% for Talia or you know, that alternative that's dramatic, because it has to correspond to reality. So sure, if we had that big a difference, it would be great, but we don't. And when you have a gigantic difference, it's pretty obvious. You don't generally have to do a lot of statistical analysis. So we have to pick an alternative that corresponds to reality. I mean, sure, if we did that, it's easy to detect it, but we don't have that big a difference. All right, so increasing n is the way to go. And increasing n, why does that separate the curves like that? Well, remember that the standard error, remember that our sampling error, our error, you know, we expect this, and our error is the spread around this. Our error gets smaller with a bigger sampler size. Remember our formula. It's sigma over root n. So as n increases, the standard error decreases, and then the curves get narrower. You get a separation. You get less error. You get less sampling error. Less overlap of the two curves. So it's easier to see a difference if it exists. Okay, so that's really where all these power calculations happen, is in designing an experiment. It's one of the most important things you need to do. You need to figure out what size sample you need to, in designing an experiment, what size sample you have to, what size experiment you have to have, how many people, if you're talking about people, do you have to have in the experiment in order to detect some kind of difference. And that goes into the planning of the experiment. It's extremely important if you ever work as a statistical consultant. That's a huge piece. If you get that wrong, then in either direction, if you say you need too many people to detect the difference, it costs a huge amount of money and you waste people's money and time, because it's hard to get that many people. If you say too little, then you might miss some real difference that exists. So it's very important to understand how many people you need to sample to achieve a certain power given a certain significance level, which will be in chapter 3 that we're doing. But in chapter 2, we're just talking about with a set number, with a set n. Once we have n given, these are calculating beta for a particular alternative, and a set n in a particular alternative, and sigma, really. And an alpha, because you're setting alpha. And sigma will be given to you. Sometimes you can calculate it. Okay, so that's the idea. Yes? Yes?
You said that we need to pick an alternative that corresponds to reality.
Yeah.
How do you decide where that cutoff is?
That's a really good question. Like, it depends on what you care about. Again, like the smallest difference that you wanted to detect. Sometimes, like in our, we don't, like in the ongoing experiment we're doing right now, I might not care if there was just a tiny edge for the online versus in class method, you know. Or let's say a good example is a flu vaccine, because if it's a mild flu and it's just gonna prevent some, you know, and it just reduces death, you know, it reduces the flu by just a very small amount, you might not care about it. But let's say it was a deadly flu and it reduces it by a tiny amount, then that would be people dying. So you would care about that small a difference to detect. So every situation is really different. It depends on what you're looking for. And that's a really important concept that's not taught in statistics, because it would be taught if you were more apprentices and really involved in projects. Then you'd be thinking about this all the time. Okay, what do I want to do here? But generally speaking, the way you're taught in school is, okay, let's just tell them it's 5%. It's easier to make problems and everybody knows it's 5% or something like that. You know what I mean? So all these issues aren't as, I'm trying to teach you as if you really cared about the problems you're solving. Because I figure, why even do statistics if you didn't? So, excellent question. Go ahead. Okay, so if a small difference really matters to you, that means these curves, you can't just slide this bottom curve out here. There might be a lot of overlap. And if a small difference is very difficult to detect, you know, just like something small is hard to see. So the only way you can see it is by decreasing your error, which could be if you're getting a better detection system somehow. If it was a smoke alarm or some kind of lie detector, you'd get a better, or a diagnostic test, it would be by getting more accuracy with your instruments. But in experiments, designing experiments, often we get more accuracy by increasing our sample size. And that's what we're talking about here. Does that make sense? Yes.
So increasing n in terms of testing the smoke detector would be like the number of times you tested it where it either falls.
No, it's a different situation there, because let's not get into that, but increasing, you'd have to actually get a better smoke detector in that situation. Okay, it doesn't correspond to this type of experiment because there's just one particular alternative. And so you'd have to get better instrumentation that can, like, you know, detect the absorption rates better and stuff. And then you'd measure that. But good question. So here we're talking about sampling error in terms of detecting, like in this, you know, not everybody's going to benefit by the online class, but if you get a huge percentage, you get a big sample, you can see, okay, is there, you can see on the average, do people benefit from one or the other? Do you see what I mean?
Yeah.
Same with cure rates for disease. If you're testing how, there's two different types of, smoke detector or a diagnostic test, all those have one specific alternative. That's not what we're talking about now. We're talking about examples where you're not testing whether somebody has the disease or not. We're testing whether something cures the disease, and we're talking about what percentage of the people it would cure. So a bigger sample will help us see that. Any other questions? Boy, you guys are so curious, amazing. We really should have a small discussion groups going on, right? Amazing. Go ahead. Yeah. Okay, so his question is this ongoing experiment that we're doing, and he said if you have a big enough n, you said? Yeah, if you have a big enough n, basically with a big enough n, any difference, no matter how insignificant to us, becomes statistically significant. So when we have a giant n, even tiny little differences are statistically significant, that doesn't mean that we really care about them that much. Okay, does that help? Any other questions? I should keep you, well, we're going to examine our own data a lot, but right now we're going to just get back to the lecture, okay? Okay. So now we did this. All right. All right, so why don't we said we could increase n here. And so let's say I wasn't happy with this type 2 error with Talia. It's 36.5%. I say, shoot, I put her through this. Do I really, that's too big. I want to reduce that type 2 error. So what if I give her 400 questions? How would that reduce it? Okay, well, will that decrease? Yes, it will definitely decrease it. And by what factor? Well, let's see. How can we think about this? Well, first of all, we have this basic formula here. And I think the easier way to see this, I wrote, is the basic formula is what? That we have this distance. The hypothesis value, the 60 minus 50, right? Let's write it this way. Divided by the standard error equals some distance in z-scores, okay? We're going to write it that way. We have that. And then we have this standard error is, this part is basically, we basically have sigma over root n. This part right here is just to change to percent, so don't get confused there. Okay, so we have this. Now what happens when we do 400 questions? Okay, well, what's going to happen? Let's see. Let's go by our steps here. The first step that we need is to find the standard error, right? Find the standard error. We can draw the picture here. This is when the null is true, and this is when the alternative is true. And we still have 50% and 60%. But I drew this picture because I already knew the standard error, right? So let's figure out the standard error here. And the standard error we said is sigma over root n. So it's going to be the same sigma of 0.5, right? We still have that 50-50 chance box, 0 and 1 equal 50-50. But now instead of the square root of 100, what do we have down here? 400, because n is now 400. That's what's changed. So do you see how that makes the standard error smaller by a factor of square root of, we quadrupled the sample size from 100 to 400, but it's only going to change the standard error by a factor of 2, square root of 2. So you'll see instead of getting 5%, we get 2.5%. Okay? So we get 0. Well, we're doing it as a percent, so we have to multiply by 100%. So we get 0.025, and that is 2.5%. Okay? 2.5%. Instead of 5%. So instead of going like, okay, here's 0, this is 1 is a z-score, right? Instead of having this be 55, what do you think it is? 52.5, right? That's one standard error. So then 2 standard errors is going to be 55, 57.5. We're going up by 2.5. And now we see that this z distance is much bigger. It's not 2, it's 4. So by what factor? By a factor of 2, it decreased this, right? By the square root of 4, which is equal to 2. All right, we're going to do the same thing. Just our roadmap here is 1. We're going to find the standard error. That's what we're doing first. Then we're going to divide this distance of 4, this distance, ZD, into 2 pieces, right? ZD is equal to Z alpha plus Z beta. That's what we're doing. That's our second step, just to remember. And then our last step, oops, I jumped to the third step, didn't I? Sorry, guys. Sorry, guys. We are going to do that because I already saw it was 4. That's why I jumped to it, right? Okay, we're supposed to calculate CD. If we didn't do it this way and see it, we'd have to calculate it. And we'd calculate it as what? Our alternative minus our null over our standard error. You see, we knew it was 4, but we didn't really calculate it. We just did it intuitively. So let's calculate it. So we're going to do 60% minus 50% over 2.5. And that's how we got that 4. It's the same thing. So if you didn't want to draw the picture out, this is the calculation. That's what you're doing. Sorry. That's all we did there. Now we're ready for this step. And this step, the third step, is finding z beta. And z beta is, we're going to just divide that up into z alpha plus z beta. And we're going to set z alpha, so then z beta will be just zd minus z alpha. All right? So we're just going to do this. So now we've got that 4. So zd is 4. And we're going to divide it into 2 pieces. Z alpha plus z beta. Right? And the bigger we make one, the smaller we make the other one. Well, if we set it, keep it at 1.65, let's just keep it the same way, then this is now huge, 2.35. And you can see that it's really big. Right? You can see here that it's really big. If we keep this at 1.65, z alpha here, we keep this at 1.65, well, then you can see the distance from here to here is 2.35. Because this whole thing, maybe it would be easier if I did it up here. You could see it better, okay? I think this is easier to see, right? So this from here to here is 1.65. And now this from here to here is 2.35, because the whole thing is 4. And this part's called z alpha, and this part's called z beta. And you see how then our type, this is kept at 5% right here. But now this part is reduced to a tiny little piece. And how can we figure that out? Do you know how we can figure that out? What are we going to look up on the table? 2.35. And we'll find out what the middle area is, and then we can find that little tail. Okay? Sounds good? All right, so let's just write that down. So we've got, see, after you go through it the first time, the second time is pretty easy. All right, so now we're going to find beta and power. All right, so we've got that. Z beta, we know is that. The absolute value of z beta is that. So we've got this picture here, and now this picture is just of the alternative. I'm just drawing this picture here, right here, this right here. It's just of the alternative, like this. And I want to know what that, when the alternative is true, I want to know what that little piece is, what my error will be. And this, from here to here, from the point of view of the alternative, is what? Negative 2.35. 2.35 is the distance. So that's negative 2.35, and that's positive 2.35, and we have to find out that. So let's just look in the back of the book. And what do we have? So we have to look at 2.35. We have 98.12. Let's just for now, just round in our 98.12. Let's just round to 98 right now. So that's, on the homework, I might ask you not to do that. Probably will, but for now, just in class, it's just easier. So this is 1%. Okay? So we have beta is equal to 1%. So power, which is 100, is equal to 99% power. That is an overpowered test. That is hugely overpowered. So 400 questions is overkill. Most people, granting agencies, you have to do this when you're applying for grants, and most granting agencies want at least 80% power. 99% would be too much. They don't want to have that big of an experiment going. All right, so any questions? Yes? Yes, it does, but they care about money. So it costs a lot to have these big experiments, to have a big sample size. So they feel like that's overkill. That's going to take too long, too costly. And we need to get this done sooner. And, they want, if you care about something happening in the real world, we said we don't need to do it that big. We don't need that much power. I mean, it depends on your situation, too. It depends, of course, on what it's not always that way.
So does looking at the power just help you determine the sample size, or does it help you determine other things?
Basically, it's mostly in designing an experiment. It's used to figure out if I want to detect something, how big an experiment do I need? That's where it's used overwhelmingly. Yep. The idea of type 1 and type 2 errors are used all the time in diagnostic tests if you're interested in medicine or anything like that. False positives, false negatives, predictive power, all that kind of stuff. But that's used daily by doctors. But that's not really the power. They're not really interested in the power. They're just interested in the probability of making a type 2 error. But it's the same idea. Any other questions? Okay. So here's a real standard problem. I skipped over something because I wanted to get to the logic, and I feel kind of bad because I know you guys seem so bright. I just don't want to shortchange you. So I'm going to, do you mind if we just go back to page 6? You got the logic down now, so you won't get confused. I just want to show you something. So when you have a null and an alternative, you have two different sampling distributions. And I drew them exactly alike. And I skipped over why I could do that. All right? I want to show you why I can. I mean, why is the sampling, why do the curves look, how do I know that under the alternative the curve would look the same way as under the null? And so what I really should do, it's going to be the same answer. But I'm just going to show you why. So it's going, okay? So basically under the null, she has a 50-50 chance. Under the alternative, you would really have to draw another probability model where she wouldn't have a 50-50 chance, but she'd have a 60-40 chance, because that's what we're hypothesizing. So let's do that. And so you draw a model where she would have a higher chance of getting a 1. It would be a 60%, 40% chance, okay? And then I'd have to calculate a new sigma, right? So sigma in this case, or the standard deviation, we're calling it sigma, would be what? Not the square root of 0.5 times 0.5, but the square root of 0.6 times 0.4. And that's just a little bit smaller than 0.5. It's like 0.49. It's approximately 0.5. And then, of course, to get the standard error, you just divide by the same square root of 100, and you'll get the same thing. So this is why, and the sampling distribution is going to be the normal curve because of the central limit theorem. So we get the same thing, and you'll just about always see the same sampling distribution, but it's because there really is this slight difference here, but people ignore it. Okay? So this would be a somewhat tiny different, it has a tiny little bit of a smaller error bars here. The same formula, this would work. You just wouldn't be able, you'd have to distribute that out. Standard error for under the null and standard error under the alternative would be different. It would just be a more complicated calculation, that's all. But it's this formula. You wouldn't be able to just divide by the same standard error like we're doing. But just about every problem I see in real practice gives the same standard error for both of them. So I just wanted to let you know that. That's all. Okay? Don't worry, in all your problems, you're going to have the same sigma for both of them. All right, now we're going back. Okay. All right, so This problem is like homework 1, number 2. So let's write that down. Okay. You have 2 problems, and this is like your second one. Okay, a large class at a large Midwestern university claims the average student only needs to spend 6 hours on their weekly homework assignments with an SD of 4. You believe the true average is much higher, at least 8 hours, with a standard deviation of 4. Okay, so you believe this. That's going to be our alternative. And the null is going to be 6 hours here. Just the standard claim by the professor. Now, the standard deviations, I said, are the same. I'm giving you the standard deviation here because this is a problem that doesn't involve proportions. So the standard deviation is not tied to the proportion or the mean. So it has to be given to you. All right. So to test their claim, you plan to randomly sample n, 25 students, from the class of 2,000, let's say, and ask them how many hours they spend on their homework per week. So here's the null. So you're testing this professor's claim. He claims it's 6, and you feel you'll sample. You don't have the time and money to sample all 2,000, but you can randomly sample 25, let's say. So you have these. So the null and the alternative would be what? So the null would be, in terms of a box model, you'd have these two. The box is the population. You'd have 2,000 tickets, and on each would be written a number. On each is written what? The number of hours the students spend. So there's 2,000 for the null box, and for the alternative, it would look just the same, 2,000. And on each is written for each of the 2,000 students, they have some number of hours that they spend studying. And the professor is claiming that the average here for the null is 6, and here we think it's at least 8. So for the alternative, we think it's 8 hours. And we think that the standard deviation is the same. So sigma in both cases is 4 hours. Okay, so that's what we have. So under the null, you'd expect x bar, which is the sample average. That's the notation for the sample average. The population average is mu. The sample is a Roman letter x, and they put that little bar meaning mean. Okay, so we'd expect this mean and average are the same thing. We'd expect this mean to be 6. And under the alternative, you'd expect 8. So that is our difference, the effect size we're trying to detect in hours. And we're going to translate it into a z-score. All right? And the typical variation of each sample average is given by that square root law of sigma over root n. So in this case, it would be 4 hours over the square root of 25, which is 0.8. So that is our standard error. Okay? So our first step right here is the standard error. Let's just write that down. So how we did that, 4 over the square root of 25, and that's 0.8. Now our second step, before we even draw the picture, we could just do it. The second step is going to be what? It's going to be, we're going to get this distance. We're going to get this, we want to translate this distance of 8 minus 6 hours. From hours, we want to translate it just to a z-score. So we say 8 minus 6 hours over our sampling error, over the standard error. These are both hours. Hours over hours, 2 over 0.8, and we get these pure units of 2.5. That is the distance in z-scores. So if we want to draw it, it would look like this. This is 6 as a z-score at 0, right? And then we'd know it's this is 8, and it's 2.5. You could check it the way we did intuitively. You could say, okay, 6.1 corresponds to 6.8. 2 corresponds at another 0.8. So you'd get 7.6. That would be 2. And then 3 would be 8.4. And our 8 is right in the middle at 2.5. You know, just when there's easy numbers, I made these easy, but usually you can't draw it so easily. So this is what you do, right? 2.5. All right, so now what are we trying to do? So our distance here, right here, this is ZD, this distance of 2.5, right? Okay. And now, what are we going to do? If we want to, the central limit theorem tells us that the sampling distribution of x bar will follow the normal curve as long as n is large enough. So let's assume the class distribution of study hours isn't too far from normal, so it will kick in after 25 draws. It doesn't matter that the class distribution itself isn't normal. This is the distribution of the average, right? So now we drew it. We did this, and this is under H naught, and now we have to draw one under H alternative. So under H alternative, it's going to be centered right here at 8. It's going to look something like that, right? This is H naught, this is H alternative. And then when we choose a cutoff, we're going to do this significance right here, the same one. When we do that, 1.65, let's do it. It'll be somewhere between 1 and 2. Right? So this part is 1.65, and then how much do we need to get to 2.5? 1.65 plus what is 2.5? So that's 0.85, right? That is ZD. That's our third step. Our third step is this, is that ZD, we're just saying ZD is equal to Z alpha plus Z beta. And so that's going to be equal to 1 point, and this is, we said, is 2.5 is equal to 1.65 plus 0.85. So that's the absolute value of Z beta. Whoops. Any questions? So we've got this. We just is that messy? Too messy for you guys? I see people straining here. Let me make it prettier so you know what I'm doing here. So I'm just trying to find this area now. Okay. And this is 5% still. I just want to find that. So how did I get it? I got the 2.5. So I said 2.5 minus 1.65 is 0.85. I just broke it up into two pieces. Once you set this to 1.65, and that's 0.85. Questions? Okay, so now to just get that area again, we're just going to find beta. We're just going to define beta and power. We're just going to look on this curve. Now, you know, there is another way to do it. We could look on a calculator. And in your homework, you might be asked to do it on a calculator. We can do that in a minute. So what are we going to do? If we look on this curve, we just go between what? 0.85 and negative 0.85. And I looked it up and I got 60%. So that would be 20%. So beta would be 20%. So beta is equal to 20%. And then your power is just going to be 80%. Because they have to add up to 100. So the power is all that. And this is your beta. But let me just show you how to do it on our calculator, because this is also what you're going to have to do on your homework. So let's go to the, did everybody finish copying this? So I can switch. Raise your hand if you want me to spend a little much, if you want me to wait a minute. It's okay. And then I'll just go to the calculator to show you. We can do the same thing. I just want you to be a little careful with the signs on your calculator, that's all. So let's go to the calculator here. So we're going to ask you, so right here there's a p-value calculator, all right? So if we wanted to do a problem like this, we have the Z-score, and we have it as 0.85, but it's negative really. It's on the left. So you should really put negative, whoops, just be careful what you're doing here. So let's say if we did negative, oh, Come on, Ellen. Okay, so negative 0.85. All right, so we have that, and that's the z-score. And what do we want to do? We want to compute the left-hand tail here. Like, we want to match it up. So you can see the picture, make sure it matches up with what you want. That would be, it's symmetrical, so you could figure out the right-hand tail too, and then not put a negative in. But just make sure, look at your picture here, and then you can compute the p-value. And it's 20. Now, this is 0.19, that's 20%, or close to 20%, 19.77%. And also be careful when you're doing your homework whether it asks you to put it in as a decimal or a percent. Okay? So don't just read this p-value off. That's 20%, or 19.77%. It might ask you to give it to 2 decimal places as a percent. So just read the directions carefully. The most important thing is you understand what you're doing, and then if you do that, then you can figure out. Okay, so pay attention to that when you're doing the homework. And office hours will start today, so if you want to come to the lab today between 4 and 6, or tomorrow between 4 and 6, I'll be down in 23 Illini Hall.